In the last video, we learned about the end behavior of exponential and logarithmic functions. And this can help us as we look at other transcendental functions and we want to start analyzing them analytically. One other thing to note, I didn't put it in here, but let me just make a comment, is that sine and cosine are wave functions, if you recall from algebra, pre-calculus, whenever you learn about sine and cosine. So these are wave functions that oscillate. Actually, if I make it a cosine and a sine, they're wave functions that are restricted between, and they oscillate, they kind of bounce between -1 and 1. So oscillate means going up and down, right? So they look like, this, roughly. I'm doing a bad job of drawing it, but bear with me here. So they're bouncing between -1 and 1, and they're restricted between -1 and 1. So they don't really go anywhere in particular. They don't have a limit at infinity per se. But that doesn't mean that we can not deal with them, because we can. So they don't actually have a limit at infinity on their own, but they can when they're combined with other things. Speaking of which, let's combine with some other things, shall we? All right, so let's look at this example right here. So we're going to find the end behaviors. And hey, cosine, just what I was just talking about. Now, I'm sorry about this. There's a typo here that I will fix for future. I'm going to renumber this. This will be example 8 for me for future. But these are both functions of t. I'm actually going to put a vertical line down the middle of my page. Use the side of my mouse pad or something. So let me pause and be right back with that. There, it's not perfect, but it helps me just kind of keep the two problems separate for myself. Okay, and actually that's a nice little hint for any worksheets you're given. It's not a bad idea to kind of try to section up the paper a little bit so you can keep the problems separate. Okay, so over here with j of t equals 3 cosine of t plus t divided by t, there's a mouthful, we want to find the end behaviors. So what that means is that we want to know what's happening as t goes to infinity or t goes to negative infinity. So let me start with letting t go to infinity just for the heck of it. Okay, so limit as t goes to infinity of 3 cosine of t over t. I'm going to rewrite this. This would be cosine of t divided by t plus, but t divided by t over here would be 1. But now I'm going to make a little bit of an argument here, like a logic argument. So this right here, this cosine of t, is restricted between -1 and 1. Right? It can never go lower than -1, never go higher than +1. It just can't. But I'm taking whatever number that is, 0.5, 0.25, 0.75, square root of 3 over 2, whatever, and I'm dividing it by infinity. Let's think about that. So a restricted number divided by infinity, that would be the limit as t, actually, wouldn't be the limit anymore because I'm kind of doing it. So it's not really a direct substitution, it's more a logic argument. But I'm taking 3 times some restricted number, right? Some number, some constant. Well, it's not really even a constant, but it's a number between -1 and 1. And I'm dividing it by infinity. And then I'm adding 1 to it. Okay, well, what's going to happen over here is whatever number this is, or actually it's infinitely many numbers, but it's restricted, right? It's going to be very, very small. It's a small number. A small number divided by infinity is big fat 0. So this is 3 times 0 plus 1, which last time I looked, 0 plus 1 is 1, and 3 times 1 is 3. So that means that I have a horizontal asymptote at y equals 3. And I just proved it analytically, more or less. All right, now I'm going to do the same thing with the negative infinity. You can probably guess where this is going. Oh, I should make a little note to ourselves. So this was the right end that I'm looking at here, right? Because I'm letting t go to infinity. Then for the left end, I'll do it down here. I'm going to let, wait for it, t go to negative infinity. Okay, so that's going to be 3. It's still going to be cosine of t over t plus 1. I mean, that little simplification I'm doing there, that's, that's just basic algebra. So then this is 3 times, but again, cosine of t is restricted, right? It can only be a number between, that's number, not hashtag. So a number between -1 and 1. So it's a small number, and I'm dividing it by negative infinity. Okay, but if I take a small number and I divide it by negative infinity, well, we learned number divided by infinity is 0 plus 1. So that would be 3 times, yet again, this is 0 plus 1, which is 3. So we actually have the same horizontal asymptote on both sides, right? So both the left and the right should be going to 3. Now it asked for asymptotes, any existing asymptotes right here, any asymptotes, which means they could be vertical or horizontal. And we're not going to have slant because this isn't a polynomial divided by a polynomial. Well, let's put it this way. If we do have any slant ones, even though they're transcendental, I don't feel like dealing with them. So we're going to just look at for vertical and horizontal for something like this. So I've got my horizontals all taken care of. My vertical's really easy because if you look at the function, you cannot have t equal to 0. There's your vertical asymptote, right? Because that would cause division by 0, and that's bad. All right, so let's look at this graph, which I, of course, have drawn in Desmos. And here it is. This is that function, believe it or not. This is what 3 cosine of t plus t divided by t looks like. And you can see that we actually cross our horizontal asymptote many, many times, infinitely many times. But the trick is that we get closer and closer and closer to it. That's the rub, right? So as we move to the left and to the right, we're getting closer and closer and closer to y equals 3, which is our horizontal asymptote. So we crisscross over first, we go really big and really small, and then smaller, closer to 3, and we get tinier and tinier as we go along. So students will sometimes ask me, can your function cross your horizontal asymptote? Absolutely it can. As a matter of fact, it can cross it infinitely many times. And that's exactly what's happening here. The vertical asymptote is also rather obvious. You can't have 0 in that middle. So that's why there's I didn't put it in there. I should add it in. So let me add in. Oop. Hold on. I just made a mess of myself. There it is right there. So x equals 0. So then I've got my vertical asymptote and my horizontal asymptote. Isn't that nice? And there we have it. So I'm going to draw that on my paper. Oops, and there it is. And I'm just going to kind of give myself a little bit of scale here. I think I was going to about -20 over here, 20 over here, -5 and 5, roughly. And then I had a vertical asymptote, so I've got to label that in there as well, which is this vertical line at the y-axis. And that would be x equals 0. Oh, t, sorry, t. T was my variable here, not x. Tomato, tomato. And then y equals 3. Perfect. So now let's go look at the other function. So we've done the cosine function. Let's look at this one. Now for this one, we are going to use that little trick that we had from the previous page. So let me bring it back up. Namely that if I have a base, like e, and I'm raising it to a power, then I know where it's going to go. It's going to go to infinity or to 0, depending on what I'm doing. Okay, so let's use that trick. But keep in mind that I know that was just for e to the x, but it'll work for e to the 0.1x as well, because 0.1 times infinity will still work out. So what I'm going to do is I'm going to multiply, right, because I want to do this analytically, your favorite and mine. So I'm going to multiply by 1 over e to the point 1t. And of course, if I do it to the numerator, I have to do it to the denominator. Keep it fair and balanced. And that means that k of t has turned into some other function. Let me rewrite it. I'm not even doing a limit yet. I'm just rewriting this function. So this is 2000 e to the point 1t over e to the point 1t divided by 10 e to the point 1t plus 5 over e to the point 1t. Okay, well up here, these are going to divide away. That just leaves us 2,000 left over in the numerator. In the denominator, these two would divide away. Here, actually, let me separate that real quick, just so you can really see it. So it's 10 e to the point 1t over e to the point 1t plus 5 e to the point 1t. Because you have to multiply both terms in that, denominator times that e to the point 1t. So that'll cause 10 e to the point 1t over e to the point 1t. Hello, those divide away again. So that's 10 plus 5 over e to the point 1t. These two functions are equivalent. Not equal, but they're equivalent to each other. And we're going to use that fact. So that means that if I want to take, let's start with the right end, because I can. So if I want to go on the right end, then I want to take the limit as t goes to infinity of that new function, 2000 over 10 plus 5 over e to the point 1t. All right, now let's think about this for a second. I'm going to let t go to infinity. So e to the infinity, let me write it, that'd be 2000 over 10 plus 5 over e to the infinity, because 0.1 times infinity is still infinity. But 5 over e to the infinity is huge. I mean, that's the kind of thing that you say, I hate you to infinity, I hate you e to the infinity power, right? It's a really huge, huge number, super, super huge. So if I take 5 and I divide it by that huge number, I'm going to get 0. You guessed it, right? So this is just 0. So that means that I've got 2000 over 10, which is 200. So I have a horizontal asymptote on the right of y equals 200. Okay, now what about the other end, the left end? So if I look at that, I'd want to let t go to negative infinity. Okay, now this isn't going to be as straightforward as you might think. So this is 2000 over 10 plus 5 over e to the point 1t. Okay, so that's 2000 over 10 plus 5 over e to the negative infinity. But a negative power causes the fraction to reciprocate, right? So this is, let me write this, 2000 over 10 plus 5 times e to the positive infinity, right? Because of the power rules, right? A negative power means that it's in the wrong place. So if it's in the denominator, you have to move it to the numerator and then get rid of the sign. But that's infinity. And 10 plus infinity, this whole thing is infinity. And 2000 divided by, let me make it clearer for you. 2000 divided by 10 plus infinity is 2000 divided by infinity, which is a big fat 0. Right? The whole thing is going to go away and make 0. Here. I made it so I was just dealing with that part. Technically, you do the whole part because the whole thing is infinity, but whatever. So that means that I have a horizontal asymptote. Did you catch it? At y equals 0. So we have two separate horizontal asymptotes. We have 200 on the right and 0 on the left. Now for vertical asymptotes, I'm just going to make a note up at the top. We actually don't have one. To make a vertical asymptote would mean that that denominator would have to be equal to 0. So I'm just going to make a note right here. Sorry, I separated this problem out. So the vertical asymptote does not exist. And that's because you can't take an exponential and make it turn negative, right? So you want it to set it equal to 0, so you would need e to the 0.1t to be equal to negative 5 over 10. That's impossible, right? Does not exist, right? Not in the real number system. There's no way to solve that for t and get a number that would work. For one thing, you'd have to take the log of both sides, and you cannot take the log of a negative, right? So there's no vertical asymptote. The vertical asymptote on this problem doesn't exist. All right, so now we need to go graph this in Desmos and give ourselves a little sketch to show our work on the paper. So here it is in Desmos. This is called the logistic growth function. And you can see it's growing. It grows slow, and then it's approaching, sure enough, 200, right? So if I let this get larger and larger and larger, it's getting closer and closer to 200 over here on the right, and getting closer and closer to 0 here on the left. And there we have it. So I would have to draw that picture on my paper. Let me go back, and there it is. Oops, sorry, I knocked that out of the way. Okay, so you can see that, and sure enough, I'm going to 200 over here on the right. I'm going to 0 over here on the left. My left and right and behaviors are matching. I've got my scale given and everything. All right, that concludes section 2.5.